Well, good morning. This is 8:32. We're 2 minutes late getting started for differential equations on Thursday, the 25th of July, 2019. Unfortunately, I'm the only one in the room, so I'll go on and get started with where we are. I'll wait until some student comes in to make the announcement. Hopefully somebody, and more than one body, will come in. So, normally I'd ask if there are any questions. However, there's nobody here to ask. So let's pick up where we left off last time. Okay, we had just finished example 4 in chapter 4, higher order differential equations. 4.3, homogeneous linear differential equations, linear equations with constant coefficients. And we had just been talking, we had done example 4, which had your auxiliary equation. Every solution came up with imaginary components, in fact, strictly imaginary components. So we came up with the solution. We said that example illustrated a special case where the auxiliary equation has repeated complex roots. Okay? Now, and of course, if there's one complex root, now this is as long as you have constant real coefficients. In fact, any real coefficients, okay? As your coefficients of the differential equation are real coefficients. Then if you do have a solution, okay, for your auxiliary equation that turns out to be, let me get my pen set up, okay, that turns out to be, say, M1 is equal to alpha plus I beta, okay, where beta is greater than 0, okay. I don't think that actually has to be the case, but they're putting it that way. And that is a complex root of multiplicity k. Okay, in other words, there are k of those identical roots, okay, just like we had in example 4. Example 4, the alpha was 0, the I was I, of course, the beta was plus 1 in 2 cases and minus 1 in the other 2 cases, okay? So that's a complex root of multiplicity k of an auxiliary equation with real coefficients. Then its conjugate, M2, which is alpha minus I beta, again with beta being greater than 0, is also a root of multiplicity k. Okay, it's also going to be 1. Okay, now from those 2k complex valued solutions, k of those from the first and k from the second, the conjugate, you can then get the following complex value solutions. Remember, e to the first one, alpha plus I beta, x, if x is the variable, it is, and then you would have also x e to the alpha plus I beta x plus, comma, x squared e to the alpha plus I beta x, and it goes on and on and on up until you reach to not k, but k minus 1, okay? And that would be x, my nose itches, to the k minus 1, e to the, alpha plus I beta x, okay? You would have, now that is k, 1s, but notice the first one doesn't have an x in it. So that's 1, 2, 3, 4. See your counters, if you're numbering these, the first one is with no x, the second one is with x to the first power, the third one is x to the second power, so the kth one would be x to the k minus 1 power. Okay? But those are k roots, root independent, linearly independent roots, but then you also have the complex conjugates, e to the minus, well, let's do it this way, alpha minus I beta x, the second one, e to the alpha minus I beta x, third one, x squared, e to the alpha minus I beta x, dot, 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 all the way up to and including x to k minus 1, again, same reason, same rationale, e to the alpha minus I beta x. Now, those are those solutions in your E form, and they have complex issues with them, okay? And we usually don't like to deal with those, but remember by Euler's formula, you can always relate these then to be, the first one would be e to the alpha x, that's what you get from that part, and then the next part would be, and now, I would go on and group them both together. They separate them in the book, so I'll do that just because they did. But I would put cosine beta x plus sine beta x, because that's, in fact, I'm going to write it that way. That's the simplest way to write it. The cosine beta x plus sine beta x. Okay? Now, that would be two solutions corresponding to those two. Okay? The next one would be e to the, x, x e to the alpha x, and again, this is multiplied both by cosine beta x plus sine beta x. Okay? Okay? The third one would be x squared e to the alpha x times cosine beta x plus sine beta x. So each of these represents the pairings like above, okay? And then you dot, dot, dot that on down to and including the x to the k minus 1, e to the alpha x times cosine beta x plus sine beta x. Okay. Now I wrote them twice, wrote them with the cosine and sine parts because the cosine part is one solution, sine part is another solution for every pairing there. The book wrote them separately, but we almost always write them like this. So this would be 2, 4, 6, 8, 10, 12, up to twice k. Okay? So, now, in example 4, our alpha was 0, and our the k was 2, and the beta was 1. Now, it says here, of course, the most difficult aspect of solving constant coefficient differential equations is finding roots of auxiliary equations of degree greater than 2. Sometimes we can try to test the auxiliary equation for rational roots. Recall that in precalculus math, if M1 is P over Q is a rational root, then of the polynomial equation, and you listed out a sub n, m to the n plus a sub n minus 1, m to the n, all the way down to a sub 2 m squared plus a sub 1 m plus a sub 0 equals 0. Enters your coefficient. then the integer p is a factor of the constant term, and the integer q is a factor of the leading coefficient. That's called the rational zeros test. If you remember that from pre-calculus algebra, if you didn't have it, let's do that in example 5. Okay, hopefully this will be a refresher, but if you never have had it before, hopefully you'll see the thing. So here's our differential equation. 3y triple prime plus 5y double prime plus 10y prime minus 4y is equal to 0. Okay. So there we have our differential equation. Now, of course, the potential solution, anytime you have constant coefficients with a linear, higher order differential equation, your assumption is y is equal to e to the mx will be a solution. And then we build the other solutions from that. Okay? Now, when you plug that in, we take up to the third derivatives here, okay? Plug it in, do the thing, you get your auxiliary equation, which is 3m cubed plus 5m squared plus 10m minus 4 is equal to 0. A cubic polynomial, and we know that has up to 3 real roots. Okay? Now, let's really dredge back into our... here he is. Right and early, huh? Okay.
Hey, I said 45, right here, 44.
Oh my goodness, am I so proud. Okay.
Your Cal 3 class ain't got that much of a crowd either.
What's that? No. Well,
Or was that a bad day?
no, it was, well, it was a little worse than maybe most days, but it's usually those people are almost always here, and then every now and then another one or two will come in.
This one was like Amazon shopping when she left.
What's that?
She was like downloading illegal movies or something. It looked sketchy. I was like, what are you doing?
Yeah. You see, that's one of the problems with e-books. I can't say you can't have your laptop up because a lot of people use an e-book. So
you got headphones on. And
yeah.
I'm sure you're listening to
Right.
a book.
Yeah, right. Yeah. But look, they're adults. You choose. If you want to pay the money and not get anything out of it, that's your that's your choice. Okay? Right. Yes.
Just a little. I'm being petty, so I'll stop.
Yeah, okay. All right, let me go over the announcements. I know you heard them yesterday, but I did think of one that I left out. So let me make sure you understand that one, and this is mostly for other people listening as well. First, have you done the student course evaluations? If not, just remember to do them. You don't have to do them now. You can even wait till you get your grade, whatever, but the deadline is 8th of August, and frankly, I'm not going to be here 8th of August to remind you, and I don't think you'll be here 8th of August to be reminded, so just don't forget to do it, please.
Yes, sir.
Okay. Now, and this is because I know you've heard just about all this. This is also for the others in the class who may be listening to with their headphones on to the class later. Here's the schedule and the procedure for the rest of the term, which there's not much left of it. Okay? First and foremost, office hours today. After this class is over at 10:45, then I have office hours from 10:45 until about 4:15. At 4:15, I'm leaving, or shortly thereafter that, to go to the Birmingham East Campus to teach my physics class. I said earlier 4:30, but I found I just can hardly make it there. Well, I can get there by 5, but then get the keys to to get the room set up and, projector on, all that kind of stuff. I was almost always late getting started. So I'm moving back to 4:15 to leave here. Okay, and then I'll be there from 5 to 6:30, and then usually it takes me close to a half hour to shut everything down. So I will be there after 6:30, but usually not past 7. All right, so that's today. Monday is the last day for Monday-Wednesday classes, and so I have office hours 8 to 8:30 in the morning. I'm in class from 8:30 to 5:25, and then have another 30 minutes office hours at the end, 5:30 to 6 o'clock. Okay, that's Monday. Tuesday, for this class, this is where the change comes. Have office hours from 8 to 8:30, but you're always here and asking questions. I realize that. Okay, that was a joke. Okay, and then we have this class, and when this class is over, that'll be sad, but when it's over, that will be our last class of the term. From 10:45 until 4:25 again, I'll be office hours here on this campus. So just like today, I'll be heading over to the Birmingham East Campus. Go from there. Okay. Now, here's the difference. Here's the difference. Not like today. I have an eye appointment. I believe it's 2 o'clock Tuesday afternoon. So I'll be in my office up until about 1:30, 1:45, and then I'm heading. It's just right across the street here at UAB West, and I'll be there. Last time I thought it was just going to be a real simple thing, and it took about 2 hours. I just sat there, okay? So this time I'm taking over papers to grade if I have any, which I think I will, and if not, I hope to be able to get on Wi-Fi and work on my computer. But that's another issue. So I will be out of the office on Tuesday from about, I'm just going to guess, 1:30 to 1:45 up until, I don't know, as soon as I can get back, okay? Then I go at 4:15 to the Birmingham East Campus, okay? So that's Tuesday. Wednesday is the first day of finals, and so therefore I'll be in the office from 8 o'clock in the morning until, unfortunately, 12:30, because we have a meeting Wednesday afternoon. I don't know why they scheduled one during finals week, but we have a meeting at 1 o'clock over on the Birmingham West Campus, so I will need to leave here by 12:30 to be there by 1, and usually the meeting goes at least, this is a long meeting, at least 2 hours or somewhere close to 2 hours, so I should be back in my office over there, which is B122, Academic Building, B122, sometime around 3 until 6. Okay. Thursday, our last day here, I'll be in the office from 8 in the morning. Now, if you get here before 8, just slide it under my door. That was a joke. Okay. And I'll be here until about 4 o'clock. I'm not saying 4:15 now because I have to pick up some other stuff to get over to the Birmingham East Campus. So I'll be there from at least 5 o'clock until 6:30. No class, so you can come and turn in anything there. Now, let me back up. I forgot this other piece. Research papers are due by Tuesday, okay? Anytime after Tuesday you turn them in, you'll be losing points. Now, in the other class, it's Monday, but in this class, it's Tuesday. What's more, I need all your tests in by Tuesday morning, because I'm returning all the tests that have been done. I'm working on the last one to be graded here. I'm almost through grading it. No, I've got one more to go after this one, and I'll be through grading those, so I need all your other tests in, because I'm returning those. I can't return your research paper, because periodically they ask for samples of student writing, so I have to hang on to those. So, that's backed up to Tuesday. Be sure you get your paper in by Tuesday. Sooner is better, today or Monday. will be perfectly fine. Tuesday will be fine too, but anything after Tuesday, you'll be losing points on your paper, and anything after Tuesday, I cannot accept a test. That makes it a big fat 0. So please get those in. All right. Now, any questions on anything we've done so far, how we're going to end the term, anything like that? All right, this is example 5 on page 139, chapter 4, higher order differential equations, 4.3, homogeneous or homogeneous linear equations with constant coefficients. And this is example 5. Here's the differential equation. 3y triple prime plus 5y double prime plus 10y prime minus 4y equals 0. Okay? Because that's a linear, ordinary differential equation with constant coefficients, our assumption is the solution is of the form y is equal to e to the mx. That's how we've done all these with constant coefficients. That assumption, when you plug it in, take the first derivative, second derivative, third derivative, and then plug it into this, you'll get the auxiliary equation of 3m cubed plus 5m squared plus 10m minus 4 equals 0. All right. Now the task at hand is to find the roots for m. When it's a quadratic, that's pretty easy. You either factor or you use the quadratic formula. When it's a cubic or higher, you don't have those options anymore. There is no cubic formula. Now, what we do is go back to pre-calculus algebra. Now, did you take that, or was that left over from high school?
I took it in college.
Okay. I don't know if you covered these kinds of things there, but the first thing I would do with an equation like that is use Descartes' rule of signs. Do you remember how that goes, or did you ever have it?
If we did, I forgot.
Okay. Here's what Descartes' rule of signs says. Look at the number of sign changes in these terms. This is plus to plus, that's not a sign change. Plus to plus, that's not a sign change. Plus to minus, one sign change. Now, what that tells you, you have one real solution. You've got to have one real solution. Guess what? We knew that anyway. Didn't we?
Yep.
How?
This is what we've been doing, I don't know.
No.
Y equals e to the mx.
No, okay. Right.
That's the
Let's look at this thing. Right here. Right? That's a cubic equation. Cubic equations, if you think of the end behavior, this is a polynomial equation. Cubic polynomial equation, and in fact, any odd degree polynomial equation. If m is very large negatively, this is a very large negative number because this 3 is positive. If m is very large positively, it's an extraordinarily large positive answer. This governs for large values. We call it end behavior. This is going to be extremely negative. That's extremely positive. Two features of a polynomial function. One, always smooth. Number two, always continuous. So therefore, if you're starting down here and ending up here, you've got to cross the x-axis somewhere. It's smooth and continuous, you got to. So you know you've got at least one real solution. Okay? This tells you you only have one real solution. Okay? Now, we're going to use that piece of information later. The second part of Descartes' rule of sign is to consider f of, or let's call it p of minus m. Okay? Well, that would change the sign of this one. That would be minus 3m cubed. It would not change the sign of the second one, because when you square a minus m, you still get m squared. So that would be plus 5m squared. It would change the sign of the next one, minus 10m, and it wouldn't change the sign of minus 4. Okay? Now, what you do here, same as before, count your number of sign changes. You have one sign change there, a second sign change there, but not a sign change there. So that means you have two, okay? or subtract 2, 0, this is positive real solutions, 2 or 0 negative real solutions. Okay? That means you could have 2 or you may have none. Okay? Now, if you had 2, that accounts for all 3 possible solutions you have. If you have no negative real solutions, that means you have 2 complex solutions. And they will be a conjugate pair. Okay? Remember that? Okay. So, that's what the Descartes rule of signs tell you. Now we go to the real test. Okay? And this is called the rational zeros test. And what you do with this one, you know if this has a rational zero, this equation. Forget about the second one now. I'm going to go on and erase it because that was just for Descartes' rule of signs. But I'm going to leave our conclusion from Descartes' rule of signs. But I'm going to take that out so you don't get confused. Okay? Not that you would get confused. Okay. What you do for the rational zeros test, if there's a rational zero for this polynomial equation, then it's going to be of the form P over Q, a ratio of 2 integers, right? Okay? Now, what are the possibilities for P over Q? The P comes from all the possible factors of that last term. Okay? The last term is a -4, so all its possible factors would be plus or minus 1, plus or minus 2, and plus or minus 4. Divided by the Q are all the possible factors of your leading coefficient. And that will be plus or minus 1 and plus or minus 3. That's it.
Why is it 1?
Because 1 will go into 3. 1 will go into 4. Those are factors of 1, 4, and 3. Okay? Now, what you do at this point,
why don't we do plus or minus 5?
Because 5 won't go, 5's not a factor of 4 or 3. It's all the possible, the numerator is all the possible factors of this, which is 1, 2, and 4, plus or minus. The only possible factors of this one are 1 and 3.
So P is equal to the last code, the last thing.
The factors of the last term, of the constant term. And Q is the factors of the leading coefficient. Okay, this is called the rational zeros test. Okay, now what we do with this, and this is how I do it anyway, some books do it slightly differently, that means here are all the possible factors. I like to start with the integers, and that would be plus or minus 1, plus or minus 2, and plus or minus 4. That's when they're divided by plus or minus 1. Then deal with the fractional forms, and they are plus or minus, we've already done, okay. The first 3 were when you put the numerator over the plus or minus 1. The next 3 are when you put it over plus or minus 3. So it would be plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. Those are all your possible zeros, rational zeros of this function. Now you know you can't have more than 3, so a lot of these you're not going to use, okay?
Oh, wait, that makes sense though. I see how you got those numbers, because you put all of them over 1 and then you put the rest of them over 3.
Yeah, right. And if you had another factor in the denominator, you put them over that. Now occasionally you'll find they repeat themselves, only put them down once.
But this,
yeah.
So are these the numbers that will make this thing 0?
That's what we're looking for, to make it equal 0, right? Now, the easiest one is usually plus 1. Now, why is that easy? If you put a plus 1 in here, all these are 1s, and you just add the coefficients.
But you get 14.
Yeah, and that's not going to work. Because you see, yeah, that's not going to be 0. So plus 1 is out of there, okay? Okay, yeah, we can do negative 1. Now, okay, here's the easiest way to do negative 1, okay? Put negative 1 on the outside. Do you remember synthetic division?
Yeah.
Okay, do you put your coefficients here, 3, 5, 10, and minus 4. That's a 10. My pen is really dragging today. Now, I always do this. I'll go back and check. I count how many terms we have. It should be one more than your degree. It is. So we've not missed a term. Then my little rule is skip a line, draw a line. I've never seen that in the book before. And then bring down the 3. And then from there you do?
Negative 3.
Yeah, negative 3. 2.
Negative 2.
Negative 2.
8.
8.
Negative 8. It won't work.
It won't work. Okay? So, negative 1 is also out.
I'll check the 2.
What's that?
See, I don't think any of the positive numbers are going to work.
Well, no, 1 is. I almost guarantee. Remember, you got 1 positive real solution. It may be that it's going to be an irrational solution, so it might not. You're right, but the odds are one of them will
It's
work.
going to have to be one of the ones in the fraction.
It could be. It certainly could be. So plus or minus 1, both of those are out of there. Okay? Let's try 2. Oops, I forgot to erase that.
So it's not the positive version of 2, so let's do negative 2.
Okay.
I can go ahead and take it to the bank that positive 2 and positive 4 ain't going to work.
Okay.
Alright, let's see. That's going to be negative 6.
Negative 6.
Positive 1. You add them?
Add them. Of course you do.
So it'd be negative 1.
Oh, I thought you said positive 1. Okay, sorry about that. Okay.
Positive 2.
Got it?
12.
12. Not going to work.
Yeah.
Okay. So negative 2 didn't work. And you don't even want to try positive 2, huh?
No.
Okay.
This is a waste of time.
All right. So we'll delete that, and that. Okay. You want to do negative 4 next?
Yeah.
Okay. Negative 4, that would be
12. Negative 12.
negative 12.
Positive 7. Or negative 7.
Okay. Negative 7.
Or positive 28.
Right. That ain't going to work.
Well, yeah.
Right. Okay. So that one's not going to work either. Okay.
1/3 is going to be a turd.
Okay. And now, I sort of meant to tell you another hint here, but I've already gone past it. So now, when you get to the fractions, are you going to want positive and negative, or what?
I mean, we're going to have to go positive and negative because one of those positives is
You figure one's going to be positive, so let's at least go until we find. But once we find one positive, don't try anymore, okay?
I'll do a positive one though real quick.
Okay. Positive what? 1/3?
I was going to just plug it in for M. Well, we could do it with the mark. We could do it with synthetic. Let's do it.
Okay. 1/3. Okay.
You're going to get 1.
1.
6.
6.
2.
2.
8. 12.
12. Okay.
Yes. It works.
Yes, it will. 4. 0. Ding, ding, ding. We got a wiener.
So it's going to be 3x, 3m, either 3m or 3m squared minus 6m, or 3m squared plus 6m plus 12.
Exactly.
I don't know if I was about to put x in 10 second one. Testing that on. It's just common. It's hard not to say x.
Okay. I know. Now, so X or M, you got me doing it now. M equal 1/3 is a root. Okay. Now, let's go back and see what else we do. That's positive. You only have one positive. Don't look for any more. But guess what? Once you get to a quadratic, don't mess with it anymore. You could do the quadratic formula from this point. So set this equal to 0.
Negative 6 plus
Wait, 1. Yeah. Okay. Second, let's fact.
6.
Okay, let's do it a little easier. Factor out a 3, and that gives you
M squared.
M squared
Plus 2m.
plus 2M
Plus 4.
plus 4. So I don't think 6 is going to work.
Why is that?
Because, try it. You'll like it. No, you won't.
It'd be 36
right?
Yeah, it wouldn't work.
No, it won't. Okay.
I mean, this one's going to be the same, anyways. Negative 2 plus or minus the square root of 4 minus.
All right, you're doing the quadratic formula. Wait, I've got his knees. You awake yet? Okay, good. All right.
You can't factor that, though.
You cannot factor it. You're absolutely right. So quadratic formula is the way to go. And what you said, negative 2 plus or minus the square root of 4 minus
that's just going to be 16.
4, yeah, 16. Okay, you're ahead of me. Okay, divided by 2. All right.
And
Now,
we get a question.
yes.
And I don't know if I'm going ahead of myself. Could you? No, because yeah, you can't do that. Sorry, I was going to say could we reduce the 2's, but you have to reduce the square root also.
We are. Let's do that. It's minus 2 plus or minus. What is 4 minus 16?
That's just going to be negative 12.
Negative 12. Okay, are there any?
It would be 2i root 3.
That's it. 2i root 3. You're good. Okay? That's something. No. Okay. Divided by 2.
So now we can take her.
Now you can take the 2's out.
So you get negative 1 plus or minus
I root 3. Okay, so your m, your 2 complex roots, and their complex conjugates of each other are minus 1 plus or minus I root 3. Okay.
Could we then break that up and say like m equals negative 1 plus I root 3 and then square root? No, we can't do that. Sorry.
What's
I'm trying
that?
to get rid of the I.
We will.
No.
Okay. In fact, that's what we did in the last example. Okay. Now, if m is a root for your characteristic equation, right? That means
Oh
that.
God, I'm about to do the alpha stuff.
Oh yes, isn't that fun? Y is equal to e to the 1/3 x. Okay. There's one solution. The other two solutions, just as you just noted, y, let's call it y2, would be what then?
What?
Say again?
All right.
Yes, you did. You just said it.
Yeah, but I forgot already.
It's short memory, okay? It's e to the minus x. There's the alpha part.
This is case 2.
And then, in fact,
ye, no. Yeah, ye negative x c1 cosine root 3.
C1, wait. C1, okay. I can't get my pen to write. C1 cosine, go on,
root 3x.
root 3x plus
or c2
C2 sine
Yeah, you know.
root 3x. There are your other two solutions.
No, it's case 2 is the formula y equals e alpha c1.
Yeah, e to the alpha x.
X plus cos c2 sine beta.
Then the imaginary parts you put as coefficients for sine and cosine.
But it's not a negative alpha, it's just we
No,
put negative x.
it was because it was a negative 1. Alpha was negative 1. Right here. Okay. There's your alpha. Your beta is root 3. All right. There are your three solutions. One real, positive. You happen to have 0 negative real solution, but that was an option from Descartes' rule of signs. Okay? And so therefore, since you only have one real, you need 3. The other 2 will be complex. Okay? Got it? All right. Now, actually, the better way to write this would have been C1 e to the 1/3 x. Let me write it here. y, this is your complete solution, your total solution here, is C1 e to the 1/3 x plus e to the minus x times C2, so I'm going to make these 2 and 3 here, cosine root 3 x plus C3 sine root 3 x. All right. So that will be your complete solution, your general solution. Okay? Now,
I thought there was 2 negative solutions.
say again?
I thought there was going to be 2 negative solutions.
No, 2 or 0, if you remember. And those are real solutions, too.
Sorry.
I don't know. No, it's all right. I don't know why my thing is going crazy on me. It did this. It usually does this on the Birmingham East campus. It's doing it now here. Okay? Remember, the Karch rule of sign said you're going to have one real solution. There it is. And I mean, now we're talking about the thing here. That was your 1/3. M equal 1/3. Your negative real solution was either going to be 2 or 0. Okay? So we're either going to find 2 negatives or we're going to find 0 negatives. We found 0 negative real solutions. Those other 2 solutions were complex. And they were these. -1 plus I root 3 and -1 minus I root 3. Both negative. So those then translate to e to the minus x, and then cosine root 3x and sine root 3x. So a linear combination of those. So that's how they usually write the answers. Okay? Notice you don't usually put a arbitrary constant in front here because they go with these. This is a common factor for both of those. So there's your solution. C1 e to the x over 3, I did 1/3 x, however you want to say it, plus e to the minus x times C2 cosine root 3x with C3 sine root 3x. All right, that was example 5. And the rest of this, they're referring to some use of computers, some Mathematica. Is that the one y'all used? Or y'all used MATLAB? Not MATLAB, was it? Or
MATLAB.
MATLAB, yeah, okay, good. And then there's also, they talk about differential, blah, blah, blah. I don't think there's anything all that crucial there. I've already assigned most of these homework exercises, any of the odds 1 through 13 that are in the back of the book, any of the odds 15 to 27 that are in the back of the book, any of the odds 29 to 35 that are in the back of the book, either 37 or 39 if they're in the back of the book, 41 if it's in the back of the book, and 43 to 47 if they're in the back of the book, and any of the odds 49 to 57 if they're in the back of the book. Now, if any of the discussion problems, odd discussion problems are back there, you can also look at those, but most of the time they are not. And then they have some on computer labs, and if you want to go back to Auburn and play with MATLAB, I know you do, you're welcome to do so.
Stop talking about it. It's traumatizing.
Okay. All right. Now, we're moving on to 4.4. Now, we either can do 4.4 or 4.5. They are 2 different ways of looking at the same
Is it like this?
issue. Huh?
Is it like this?
Is it like what?
Is it easy like this?
Pretty much. I find that 4.4 is a little more direct. See, what do you do if you have undetermined coefficients? That's what the title is. 4.4 is undetermined coefficients, a superposition approach. 4.5 is undetermined coefficients, an annihilator approach. You can do either one of them, but there's not really any reason to do them both. Unless you're just interested, but I'll leave that up to you if you're that interested. I've taught them both ways, and it seems like to me the students pick up on superposition more easily. So that's what we're going to do, 4.4. We're going to skip 4.5 and then hopefully get into 4.6. Okay? Oh, one other thing. I should have said this at the beginning, and if anyone else comes in, I'll say it again. I do have your final exam ready. We haven't covered everything in it, but we have today and Tuesday to do that. Hopefully we'll get that far.
I can pick it up Tuesday if it's...
Well, you can get it today if you want
I
to.
want to be honorable, though. I haven't turned in the second test, so...
Okay, well, you can still be honorable and take them both, in case you have extra time this weekend after you finish the second test to work on the third one.
Okay.
Is that honorable enough?
I was trying to be honorable to your rule.
Yeah. Did I have a rule?
You said you can't give out a...
Oh, let's see. Well, yeah, that was in the regular term. I don't want you crushed during finals week, so I'll waive that honor issue, okay? And you can do it. All right, well, I appreciate it. All right, so let's get started on 4.4. Let me erase the ink here. You don't need that anymore, do you? Let's see. Is it still that cold or allergies or what?
No, I think it's just a little bit... I've been having reflux the last week. So it's mostly just like reflux. It's like mucus. I think it's Sudafed, though.
Think it's what?
Sudafed.
Sudafed. Oh, yeah, you're taking that.
Sudafedrin?
Yeah, right. Pseudoephedrine. Yeah.
Pseudoephedrine. Oh,
Right.
I tried. It's a big word.
Right. All right. So let's look at 4.4, undetermined coefficients, the superposition approach. All right. Now, to solve a non-homogeneous linear differential equation, now the difference from what we were doing, this one looks like this. A sub n, y, the nth derivative of y, plus a sub n minus 1 times the n minus first derivative of y plus a sub n minus 2 times y, the n minus second derivative of y, plus dot, 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 plus go down to a sub 3 y triple prime plus a sub 2 y double prime plus a sub 1 y prime, sorry, prime in the wrong place. Okay, plus a sub 0 y equal non-homogeneous or homogeneous or however you want to call it, you would have some g of x out here. Now that g of x can be any function of x. It can be a single function of x, it can be multiple functions of x, it can be any functions of x. Just can't have any y's in it at all, okay? But it can have any x's in any form whatsoever. Sort of, okay. Now, here's the two steps you do. First, find the homogeneous function y sub c. Okay, I'm just going to do y sub c. Now, what is y sub c? What we just did, remember, notice these are all constant coefficients, okay? But you put a 0 here, right?
Yep.
So you do your y is equal to mx. Go to town with that. See if you can find your auxiliary equation. Once you find your auxiliary equation, find the solutions for y. Use all the tools in your belt to try to find those solutions for m. Okay? Then once you find those solutions, plug them in to your general solution. Now, it's no longer called a general solution, it's called a complementary solution, y sub c, because you still got to deal with the g of x. So the first part is find the complementary solution, y sub c. The second part is find any particular solution. I'm just going to call it y sub p, particular solution of the non-homogeneous equation. Okay? So particular solutions there. Now, bless you. Okay. Just a little note here. Your complementary solution will have n arbitrary coefficients. C sub 1, C sub 2, C sub 3, C, just like that last one had 3. It was a third degree polynomial. Third degree, third order linear differential equation. You had 3 arbitrary coefficients. Y sub c here will have n arbitrary coefficients. When you find the particular solutions, those do not have arbitrary coefficients. You just put the solutions down, okay, without those, okay, without arbitrary coefficients, okay. Then your general solution, I guess this is the third part, y is equal to y sub c plus y sub p. Okay? Now, the complementary solution function, y sub c, is when you have the y sub c is when this is equal to 0. The g is equal to 0. Okay? And we just did those. Now, the method of undetermined coefficients, that's what we're doing in this section. The first of 2 ways we should consider for doing obtaining the particular solution. So this is focusing on what you do here. We know how to find the complementary solution. We just did, 4.3. Now we are finding the y sub p's. Okay? For the non-homogeneous or homogeneous linear differential equation is the method of undetermined coefficients. The underlying idea behind the method is a conjecture of the form of what the y sub p is going to be. You make some guesses, an educated guess really, motivated by the kinds of functions that make up your g. Okay? That's where the y sub p, that's based on that g of x. Okay? Now, the general method is limited to linear differential equations, such as this one I have there, where all the coefficients, a sub i's, are constants. These are not functions of x. These are all constants, just numbers. Okay? Okay? So there's the first thing. G of x, now here's the key, a key. G of x is limited to certain functions. It could be a constant. This is your g now. A constant k. It could be any polynomial function. Okay? Any polynomial function. It could be any exponential function, e to the alpha x. Now that's not necessarily the same alpha as we had before, but they just used that for some reason. It could be a sine or a cosine. Not necessarily the betas, but just a sine or a cosine. What's that? Oh, okay.
I'm so sorry.
Yeah, no problem. Okay. And they still put in a beta x, but it's not necessarily the beta x that we had before. It could be, but it doesn't have to be. Okay? It could be finite sums or products of these functions. Okay? Of any of the above. Okay? So therefore, it could be constant plus e to the x. It could be a polynomial times e to the x. It could be a sine or a cosine times a constant. It could be any sum or product of any of those. Okay? Now notice what it can't be. It can't be a log function.
I'm cool with that. I'm 100%
Okay.
awesome with that.
Good deal. Okay? It can't be a rational function.
No square roots.
No square roots. You okay with that too? All right.
I guess.
All right. Well, I'll make you be it. Okay. So I'll force you to. Okay. Now. Okay. Now, the note to instructors at the bottom of the page. In this section, the method of undetermined coefficients developed from a viewpoint of superposition principle. In the next section, it's an entirely different approach using the concept of differential annihilator operator. Take your pick. I'm picking this one. It just seems like students respond to this one better. Okay. Now, as they say here, the constant coefficient is a polynomial function, so that seems like that's a little redundant, okay? But just to emphasize, it can just be a number, okay? So, whatever. Now, the following functions are some types of the inputs g of x that are appropriate. Your g of x could equal 10, or any other constant in the world, negative pi thirds. Doesn't matter, okay? Your g of x could be any polynomial function, x squared minus 5x. That would be perfectly fine. Or any other polynomial, 15 terms, whatever. It could be g of x could equal 15x minus 6 plus 8 to e to the negative x. Okay, why? That's a polynomial function added to an exponential function. Fine. Anything like that would do. Okay? Here's another. It could be, I mean, there's an infinite number of these. It could be g of x, could be a sine 3x minus, goodness gracious, minus 5x times the cosine of 2x. Okay. All right. G of x should be any of these. Now, how does this one come into play? It's a sum of two sine and cosine function, but this one is also a product of a polynomial times a cosine function. Notice these arguments of the trig functions don't even have to be the same. One could be a 3x, another a 2x. It doesn't really matter. 17x, it doesn't matter. Pi thirds x, whatever. Okay. And how about this one? This would be legal too. G of x is equal to, what's that? I know. It's, guess what? It's the cheapest package they could find. And I'm stuck with it. I used to use one called Tegrity, which was really powerful. And I never had these kind of problems of things flicking out on me and stuff like that. But they said it was too expensive. Let's go with something cheaper. It's just as good. Yeah, right.
Yeah, sure.
Huh?
Yeah, fiat's the same thing as Lamborghinis.
Yeah.
They're both Italian.
Yes, exactly. All right. You're a cynic, I can tell. Okay. Here we have x, polynomial function, e to the x, exponential function, product, sine x, trig function. Now, it's not just any old trig function, either sine or cosine, plus polynomial function, 3x squared minus 1, times, oh my word, for some reason, even though I've been plugged in all morning and everything's fine, now the battery is showing red. And it's still charging.
What adds HP does that?
What's that?
What adds HP does that? The battery doesn't hold charge at all.
Right.
It's plugged in.
Right. Yeah, I have to too, but usually it won't. If the plug doesn't make good contact, then the light comes on. As far as I know, the plugs make good contact all day because it's still on, but it's showing red light. That drives. Well, this is a computer problem. This isn't a package problem. Okay. and it keeps making those silly little noises. Okay, this is times e to the minus 4x. Okay, now these are just made up possibilities. They're almost endless. Any product or sum of any of those, polynomial functions, constant functions, exponential functions, sine or cosine functions, any product or sum of any of those. Okay, that's what your G's can be. Okay. Okay. It bugs me that it's making all these stupid noises. You may not be able to hear them, but I can. But, I mean, the light isn't even flickering, but it's just making the noises. So, G of x is a linear combination of functions of this type. It seems like we've already hit all those. I'm not going to write them all down. Now, the method of undetermined coefficients is not applicable to functions of this form. These are not, okay? G of x equal log x, your favorite. That can't happen, okay? G of x equal 1 over x. That can't happen, that's the rational function. G of x equal tan x. Okay? That can't happen either. But you might say, wait a minute. Isn't that a product of sines and cosines? No, it isn't. It's a quotient of sine and cosine, not a product. And you can't do 1 over cosine either. That would not be allowed. Okay? And then, I know this one will upset you as well. It can't be G of x cannot equal, in fact, I'm going to go on and put here, just so it'll be clear. Cannot equal log, cannot equal thing, cannot equal tangent, and cannot equal inverse functions, like inverse sine. No, not allowed. Sine, yes. Inverse sine, no. Sine and cosine, yes. Tangent, no. Polynomial function, yes. Rational functions, no. Exponential functions, yes. Log functions, no. Okay. So that's what they can and can't be. All right. Now, let's do example 1. All right. Example 1. Solve this. Y double prime plus 4y prime minus 2y is equal to 2x squared minus 3x plus 6. Okay. There, your g of x is a polynomial function. Just a polynomial function. Where would you begin?
Make it an M? No.
Yeah, well, you will, but actually the first step is to just look at the auxiliary equation. Well, not auxiliary equation. The homogeneous equation, which is y double prime plus 4y prime minus 2y equal what? 0. Got it. Now you do, for this one, let y equal e to the mx. And that produces your auxiliary equation. And what's it?
M squared plus 4m minus 2.
Equals 0. Okay? Think you can factor that? It's a quadratic.
Yeah, quadratic formula.
Yeah, quadratic formula. Can't factor it, quadratic formula. M is equal to?
Plus or minus. I'm sorry, hold up.
Negative 4
plus
or minus the square root of
16
minus 8
over 2
over 2.
equal to
That has a 4 hiding in it, right? 2 root 2. Whoa, goodness gracious. My pen just decided to go out on me. 2 root. Goodness gracious, this thing is aggravating.
So I got -2 plus or minus root 2.
2 root 2 over 2, which you're absolutely right, minus 2. Okay, so it's minus 2 plus or minus 2 root 2. I mean root 2. Okay. All right. Now, what would then be your complementary solution? Y sub c, that's the one of the homogeneous or homogeneous case. That would be what?
Y of c equals...
Yes, you do.
Okay.
You do.
Is it going to be
E to the
-2x?
-2x. You knew it. I knew you did.
That's not imaginary.
No, we're getting rid of that. Wait. Oh, wait. No, you're right. I'm sorry. Well, I could have left it Y sub c. These are just real numbers, okay? So what would this be? This is your m. It's not imaginary. You're absolutely right. So what this would be, written another way, -2 plus root 2 or -2 minus root 2, okay? So that would be y sub c is equal to, you go back up here, e to the -2 plus root 2 x, C1, that, plus C2, e to the -2 minus C1, root 2 x. Okay. Now, there are some things you can do with this, okay? Before I take you too far down the... Whoa, we messed up something here. I was listening to you and maybe not paying enough attention. Did I write something down wrong? How did they get a root 6 here? It's -4 plus or minus 4 squared, which is 16, minus 4ac, and 4 times minus 4ac. C is negative. That's a plus there. So let's back up here. I shouldn't listen to you. Okay. Whoops, that one would have been okay. Let's just... Okay. I think I've got them all erased. Okay? So this would be -4 plus or minus the square root of 24 over 2. And you could factor out, again, a 4 there, so it would be 2 root 6. So plus or minus, -2 plus or minus 2 root 6. And I messed those up too. 6 and 6. Okay. I wish I could. Oh, see, I know what's happened now. While I wasn't paying attention, that does go out. Why it's doing that, I'm not sure. Okay. So this will be M1 equal that, and M2 This is driving me nuts. Equal that. Okay. I can't make it stop.
Is it just moving on its own?
Huh? See, the battery it's plugged in, and it's good. There's nothing wrong with this, except I have a bad connection here. I know that, but my battery light is on. Yeah, you just turned it off. Okay.
We unplug it for like a second, or will it turn off?
It stays on. Like right now, it's on.
Can I unplug it for like a second?
Okay.
Or will it die?
No, it won't. Okay, it's not plugged in now. Okay. Still not connected. Come on. You need to make it. Okay. I played with it enough, I know. You have to sort of turn it up here. There it is. Back on again. But, well, I think it's a better connection now because it's not making the little noises. But anyway, this is what you got. Okay? So your complementary solution are these. Okay? Thank you. The magic touch. Okay? Now, there are some other things you could do with that, but there's no real reason to. So we'll leave it just like that. Now, step 2. Because the function g of x is this polynomial function, okay, and it happens to be a quadratic polynomial function, let's assume that your particular solution, oh, this is just an assumption, y sub p is some other second-order quadratic polynomial. And we'll assume ax squared plus bx plus c. Okay? There's our assumption, that your particular solution that will produce this g of x will be that. Okay? Now, if that particular solution does work, then what we have to do is do our yp prime, which would be what? 2ax plus b, and our y particular double prime would be would be 2a. Right. Oh, okay. Now, we plug that into our equation up here. So this will be 2a, that's your y double prime, y particular double prime, plus 4 times y prime, y particular prime, which would be 2ax plus b, minus 2 times your y particular, which would be ax squared plus bx plus c. Okay? And we want this to equal to 2x squared minus 3x plus 6. Do you follow that?
Yes, sir.
Okay. Now, here we did our y particular here, and we plug that in there, plus 4 times your y prime, particular prime, minus 2 times your y particular, okay? And we want it to equal that, okay? So let's do the algebra required here. This would be 2a. What's next?
2a plus 8a.
8ax plus 4b, or not 4b, okay? Next?
2ax
minus 2ax squared. Say again? Minus 2 bx. Next.
Plus
At
or minus 2c.
2c, and supposedly that's equal to 2x squared minus 3x plus 6. Okay. Now, at this point, let's start looking at like terms on either side. Now, you could combine them first, but I'm going to wait and do that for just a minute, because here I see that minus 2ax has to equal 2. Those are only x squared terms, right? So if those two are equal, minus 2ax squared has to equal 2x squared. So that tells us minus 2a is equal to 2. Okay, so what is a?
So 2a. It's going to be negative 1.
Negative 1. Okay, we got our a. All right, now.
We could plug in for
Yeah.
negative 1.
So let's do this. That would be a minus 2.
Could we plug in the a into the YP1, or we'd have to plug into the general?
Say that one more time.
Could we plug in a equals negative 1 in YP prime?
Okay, we don't need to go back and do that. Let's do it here.
Okay.
Right there, okay? Minus 2a minus 8x. Now, we don't know the b yet, so let's leave that alone. Plus 4b. But what I do want to do is combine that with our other constant, which will be a minus 2c. Okay?
And minus 2bx.
And this will be
2bx.
yeah, we can just eliminate those, yeah. And this will be minus 2bx, so let's put that with this one, minus 2bx, okay? And that's supposed to equal negative 3x minus 6. Okay? Now, sorry, I should have combined this 2 with that one, sorry. We'll do it in a minute. So factor out the x here, and you have minus 8 minus 2b, right, times x, right? And that has to equal minus 3x, right? So in other words, minus 8 minus 2b has to equal minus 3. Minus 8 minus 2b has to equal minus 3.
Why is it minus 8?
Because that's...
Or what did you do with that negative 2? Like, I see that negative 2. You have it pointed straight at the 4b.
Okay. That's a constant term, and these are constant terms, so I'm going to pull these together later. So I'm leaving just the x terms here. It's minus 8
Minus 2bx.
minus 2b, minus 8x minus 2bx. That means minus 8 minus 2b times x has to equal minus 3x.
Yeah.
Okay, so I did away with the x's, so I have that. So let's solve for b.
It's going to be negative 2b equals 5.
Okay, so negative 2b is equal to 5.
B equals 5 over negative, or, yeah, 5 over negative.
Negative 5 halves. Is that okay? I don't know why the 5 didn't show up there, but it didn't. Okay. Is that right then?
Yeah.
All right. Let me just... Yeah, okay. Everything's going okay. That seemed like such a weird number. I want to make sure I was right on it. So then for the C part, let's plug in what we know here. And that's where I put these two together. So negative 2, and then you got plus 4b, but b is minus 5 halves. So the 2 will go in the 4.
It's 10, negative 10.
Negative 10, perfect. Minus 10 minus 2c is equal to minus 6, right? Okay? So that'll be minus 12. Add that to both sides, you get 6. So minus 2c is equal to 6.
Negative 3.
So c is equal to negative 3. All right.
So would we plug that back into the YP now?
Yes, you're absolutely right. Now, so let's do it here. Yp is equal to
Negative x squared
negative x squared
plus
negative 5 over 2x
plus
minus 3. Okay? Now your general solution, y, is equal to your complementary solution, which was right here. So that would be c1 e to the minus 2 plus root 6 x, okay, plus c2 e to the minus 2 minus root 6 x minus x squared minus 5 halves x minus 3. There's your solution, if you'll ever get to see it, okay? Because that's your particular solution. Okay, let's see how the book did. C1 e to the minus 2 plus root 6x plus C2 e to the minus 2 minus root. Oh, I see what they did. They made this a minus 2 plus root 6x. We've got the same answers. They just don't look quite the same, but it is. Then minus x squared minus 5 halves x. Minus 9? Oh, I was letting you do my math for me again. Let's see.
what I messed up?
I don't know. It seems like everything. Okay? Let's see. You had a minus 2 from there. And minus 10 there, minus 2c there, and that's equal to minus 6. No, it's not. This thing is still driving me crazy. My screen is just strobing on me, and it just drives my eyes nuts. That's a plus 6 up there, not a minus 6. Okay? Somehow that translated to a minus 6. It's a plus 6, so that's equal to plus 6. So this would be 12 plus 6 is 18. Okay. So C is equal to minus 9. So there it is. All right. All right, now it's done. Okay. There is our solution. Your general solution is YC plus YP, which is C1 e to the, and they wrote it differently, but it's the same answer, plus C2 e to the other thing, minus x squared minus 5 halves x minus 9. All right. You okay for a break?
Yes.
Me too. All right, so let's, do you need this up here any longer? Okay, so let me go on and erase this. All right, and I'll put this on the whole time. No, okay, good. No. Couldn't remember if I did or not. Okay, let's move on to example 2. Find a particular solution for this second order linear differential equation. Y double prime minus y prime plus y equal to sine 3x. All right. Now, time out for just a moment. The last time the g of x was a polynomial. So the undetermined coefficient that we did was a polynomial of the same degree. Okay? But be sure you include every term of the polynomial in that. Okay. Now, this time it's a sine function. Okay? Now, okay. I'm sorry. All it says is find the particular solution. Because we know what to do with the complementary solution, right? We did that last time. So let's just guess for the particular solution. Do you want to hazard a guess to begin with? Y sub p. Okay. Well, if you think about it and try, okay, we have an undetermined coefficient, that's why we call it that, a, and it could be a sine of 3x, but it could also be b times cosine of 3x, okay? Now, why did I use the 3x? Well, when we do our first and second derivatives, you're not going to change that. So why introduce another x or a 2x or a 17x? That's not going to work. So keep the argument the same. But why did I include a cosine here, and why couldn't I just do a sine? Because when you take a derivative, you're going to get cosines and or sines. So you need both of them. Okay? And then we'll let the rest of it play out. So guess what the next step would be?
Take derivative.
Take a derivative. And what would that be? 3
Cosine.
A cosine. Right?
Yeah.
3x. Next.
Plus.
A
Minus.
3b
Sine.
sine 3x. Excellent. Then what? Y double prime, the particular, would be
Negative
9 a sine 3x minus 9 b cosine 3x. All right. Now, let's plug all those things in to our equation up there and set it equal to 2 sine 3x. So this will be minus 9a sine 3x minus 9b cosine 3x. And then we're going to negate the first derivative, so that would be a minus 3a cosine 3x plus 3b sine 3x, correct?
Yeah.
And then finally, plus a sine 3x plus b cosine 3x, and we hope that's equal to 2 sine 3x. Okay? All right. Now, if that's the case, let's get all our signs together, and that would be a minus 9a sine 3x plus 3b sine 3x plus a sine 3x equal 2 sine, well, I don't have to write this, sine 3x.
What are you doing? Are you just...
Okay. Okay. I'm looking at all those terms that deal with signs. Okay? And I'm just not even going to write down the sign. That'd be minus 9a plus 3b plus a equal 2. Right? Yay or nay?
Yeah.
Okay. So that gives us negative 8a plus 3b is equal to 2. Agreed? Okay. Now let's look at the cosine terms. This will be a minus 9b minus 3a plus b. What did that better equal?
So what are you doing?
Okay, I'm looking at the cosine terms. Minus 9b minus 3a plus plus b is equal to what? What's your cosine terms on that side?
It would just, negative 9b
Yeah, negative 9b minus 3a plus b is equal to what? What's your cosine? 0, exactly. Okay, so this is 0. So that gives us a negative 3a minus 8b is equal to 0. Okay? Now that's called a system of equations. You remember how to solve these. All right, here's Daniel. Now, I kind of hate to do this, but I want to make sure everybody hears it. So I'm going to do a little quick timeout here and make those announcements again.
Pause it.
No, I want to record it. Yeah. In case anyone comes in and doesn't listen to the first part. Have you done the city course evaluations yet? If not, please do them before August 8th. I'm not going to be here on August 8th to remind you, so I do it before then. Okay. All right. So that's that. Number 2 is let's talk about how we are going to end up the term. Okay? I have office hours today, after this class is over with, from 10:45 until about 4:15 when I have to leave and go to the Birmingham East Campus. Okay? That's today. Okay? Monday, the last day of class for Monday, Wednesday classes. So I have office hours from 8 to 8:30. I'm in class from 8:30 until 5:25. Office hours from 5:30 to 6. That's Monday. Last day of class for Monday, Wednesday. Tuesday, we have class in here. So I have office hours 8 to 8:30. We have class 8:30 to 10:45. And then I have office hours from 10:45, unfortunately, only until about 1:30 or 1:45 because I have a doctor's appointment on Tuesday. So I'll be across the road at the UAB West. And as soon as I'm through with that, I'll be back here. But then I'll only be here till 4:15 because I've got to drive back to the Birmingham East Campus for my last class there. Okay? So I have that doctor's appointment, eye appointment on Tuesday at 2. Last time it took about 2 hours. Hopefully it won't take that long this time. All right. So that's the last, yes.
What room will you be on the East Campus?
In the nursing, okay. All right. On Tuesday and Thursday, close to 5 o'clock until after 6:30, I'm in the nursing building on the East Campus, and that's the Ethel Hall building on the second floor, 214. 214. Okay. Now, that's for Tuesdays and Thursdays. Basically from a little before 5 until a little after 6:30.
Okay, so
Now,
is nursing at the hall building 213?
214. Okay. Now, That gets me through the last day of class, Tuesday, okay? Wednesday is the first day of finals, okay? So I will be in my office in this campus from 8 in the morning, unfortunately, only until about 12:30, because they've called a meeting at 1 o'clock on the Birmingham West campus. So I'll be over there, and I'm just guessing the meeting is probably going to go close to 2 hours. Let's just say 1 to 3, okay? But I'm not going to drive back here on Wednesday. I'll just stay over there and work there. So I'll be in Dr. Pruitt's office. That's in B122 from about 3 to 6, okay? That's on Wednesday. Then I'll be back here Thursday morning, and time out. Wait, let me back up some. The last day of class in here, which is Tuesday, 8:30 to 10:45, that's when all your tests have to be turned in, and your paper has to be turned in, because I'm returning the tests on that time. That's the first 2 tests, and I can't return your papers, but anything after Tuesday, you start losing points. So be sure you get all your tests and papers in by Tuesday morning, okay, when we're in this class, okay? Now, let's get back to Thursday. Thursday of next week, on this campus from 8 in the morning until around 4 o'clock in the afternoon. At 4 o'clock, I've got to pick up a couple things and go to the Birmingham East Campus again. So again, I'll be in the nursing building, Ethel Hall building, on the Birmingham East Campus. Not this Ethel Hall building, one over there. And that's from a little before 5 until after 6:30. Now, there's no class then, so that's a good day to come over and turn things in. Now, I forgot to say this earlier, so Nolan, this will be for you too, but you probably heard it yesterday. I haven't gotten permission yet, but I'm going to request leave for the next Monday. So that means if I do not have work by all your stuff in by the time I leave this campus about 4 o'clock on Thursday afternoon, or you get it to me over there before 6:30 on Thursday afternoon at the Birmingham East Campus, I won't have your stuff. You'll be getting it incomplete for the course. And if you come and turn it in, slide it on my door or whatever, when I get back, I'll grade it and then change the I to whatever. So
You said this Monday.
Say again?
Yeah, this Monday.
Okay. No. Okay. This Monday is the last day of class for Monday, Wednesday classes. This coming Tuesday is the last day of class for this class, Tuesday, Thursday classes. Wednesday is finals day for the Monday, Wednesday classes. You can turn it in anytime Wednesday. Anytime. I'll be on this campus from 8 in the morning until about 12:30. Then I have to go to the Birmingham West campus for a meeting, and I'll stay over there. But if you turn it in on this campus later, slide it under my door. I'll be back here on Thursday morning. So that's no problem. It's Thursday I'm talking about. Thursday of next week, 1 week from today, I'll be on this campus from 8 in the morning until 4 in the afternoon. Turn in any work to me then. That'll be great. Sometime shortly after 4, I've got to head to the Birmingham East Campus. I'll be there until a little after 6:30. You can turn it in to me there. But if you slide it on my door after 4 o'clock on Thursday, or miss me over on the Birmingham East Campus after 6:30, I'm not going to see it. I'm not going to be back here, I don't think, on Monday morning, so I won't be able to grade it at the last minute. You're getting an incomplete. Okay? All right. So, did want to mention that. Okay. That's research papers and last tests. Okay. And I'll be giving you today your final exam for this one. We haven't covered all the material on it, but we'll do it, and then Tuesday we'll finish the material, and I'll tell you which questions you can ignore or whatever. But I'll give it to you today so you can start working on it over the weekend. Okay. But I need all your other tests. Okay. All right. Now, we were working on, okay. This is example 2 on page 144, chapter 4, higher order differential equations, 4.4, undetermined coefficients, superposition approach. Okay. Now, here's what we've got. We had worked through this deal. We had assumed our particular solution. Now, they're not saying we solve the whole thing, just find the particular solution. We're assuming the particular solution because your g of x is 2 sine 3x. The y sub p, particular solution, has to be any function that could produce a sine 3x. And that could be a cosine 3x or a sine 3x. So our particular solution would be undetermined coefficient a sine 3x plus b cosine 3x. Then we did the first derivative, we did the second derivative for that particular solution. Then we put those all together and wrote them out and came out with what our coefficients, undetermined coefficients for the sines were, undetermined coefficients for the cosine. It gave us a system of equations. Where do we go from here? Anybody? Where do we go from here?
We solve for B.
How?
Well, we set those two equations equal to each other?
I don't think so, because this one's equal to 2, that one's equal to 0, and 2's not equal to 0.
What if you move the 2 over and make it negative 8a plus 3b minus 2 equals 0?
Okay, you could do that. Then you would have one equation with 2 unknowns. That would be tough, wouldn't it?
Yep.
But there's something else you can do. It's almost along those lines. Not quite, but close. Okay? Any idea? Yes, you do. Okay? Multiply the top equation by 8 and the bottom equation by 3. Now, why did I sort of arbitrarily do that? Well, I looked at these two, and these had same signs, these had opposite signs. I go with the opposite sign. And if we multiply this by 8, that gives me a plus 24b, right? If I multiply this one by 3, that gives me a minus 24b. Then you can add the two equations to each other, and you eliminate the b. That's called elimination by addition. So the first equation will be minus 64a plus 24b is equal to 16, right? What would the second equation be?
9a.
Minus 9a minus 24b
0.
equals 0. Okay? Now you can add the two equations to each other, and doing that will eliminate your b, right? Yay or nay?
Yeah.
Okay, yay. All right. When you add these two together, you get minus 73a is equal to 16. So what is a equal to? Such an ugly number. Negative 16/73. Couldn't they have come up with a better thing than that? I guess not. Okay? Now, if a is equal to negative 16/73, then let's use either one of these equations to figure out what b is. Well, let's go back to the second equation here, which is minus 3 times a, which is minus 16/73, minus 8b is equal to 0. Okay? Now, if I multiply those two together, I get positive 48/73, right? And I'm going to move the 8b to the other side and make it equal to 8b. Okay? Well, I want to know what b is, so I'm going to divide both sides by 8. And that will make a 6 here. So I get b is equal to 6/73. Okay? So, what is my particular solution? Y sub p is equal to minus 16/73 sine 3x plus 6/73. No.
16.
Yeah, that's right. Cosine.
Wait,
3x.
Negative though? So
Say again?
Shouldn't that be negative instead of a plus?
Why?
Because it's a negative. Oh, never mind. I'm sorry.
Okay. It may be, but I need to know
I
why.
didn't know we solved for b. That's my fault.
Okay. So they rewrote it in a different order. They wrote the cosine first. 6/73 cosine 3x minus 16/73 sine 3x. Yes.
That's my fault. I see.
Badly? Okay, no, I'm just kidding. Okay. Now,
Now we solve for x.
second?
Now we
No. That's it. There's your particular solution. Done. Okay? We didn't do the complementary solution, but that was a piece of cake, right? Yes, right? Okay, good. Okay. It would have been irrational numbers, I think. But anyway. Can I go and erase example 2?
Yes, sir.
Okay. So, let's move on to example 3, page 145. Solve this. Y double prime minus 2y prime minus 3y is equal to 4x minus 5 plus 6x e to the 2x. Okay. Now, where would you begin?
M.
Okay. Actually, before m, I would do
Y prime minus
y double prime
minus 3y equals 0.
minus 2y prime minus 3y is equal to 0. We call that the complementary solution.
I
Okay?
thought that was homogeneous.
What's that?
Does that not make it a homogeneous?
Yes. That makes it, you're solving the homogeneous or homogeneous one. And here is where you assume y is equal to e to the mx. And what will your auxiliary equation be?
M squared.
M squared
2M
minus 2m
minus 3.
minus 3 is equal to 0. All right? Can you think of anything to do with that?
Yeah.
What?
M minus 3, M plus 1.
And that's equal to 0. And what would that give you?
M is equal to 3 and negative 1.
And what would you do with that?
Y equals
Y sub c equals
Y sub c equals C1
c1
e to the 3x
3x
C2
plus c2
e to the negative x.
to the negative x. Got it. We've got our complementary solution right there from the homogeneous part and your auxiliary solution equation, all that. Okay. Now the tough part comes. What in the world can we use for our particular? Well, here's what a first guess would be. Y sub p. Now, this has a, goodness, well, I'm going polynomial part. So let's say ax plus by. I mean b. Ax plus b, not y. Okay, where did that come from? Okay. All right. That's certainly a part of it because that would give you that part. Okay. But what in the world could we be doing with that? Okay. Well, at least we need a plus c least we need a cx e to the 2x, okay? But do we need anything else? Okay, well, let's first get with what? The complementary solution. They exchanged C1 and C2 with what we did, but it doesn't really matter. C1 e to the minus x plus C2 e to the 3x. That doesn't matter. Okay, next, the presence of 4x minus 5 suggests a particular solution including a linear polynomial, which we did. Furthermore, because the derivative of the product of x e to the 2x is going to produce x e to the 2x and an e to the 2x, we're going to need also a d e to the 2x. Okay? Now, so our g of x is made up of a polynomial and exponentials, and correspondingly the superposition principle for non-homogeneous or homogeneous equations, theorem 4.1.7, which is back there quite a ways, suggests that we seek a particular solution made up of the sum of these. The first one's going to be an ax plus b, the second one a cx e to the 2x, and then they skip the d because that also could be a differential operator. They make that a capital E, which I find a little confusing because then you say EE to the 2x, which is okay. It just sounds strange. Okay. So what do we do with that particular solution, or at least our guess at the particular solution?
Take a derivative.
Take a derivative. Sounds like a winner to me. Yp prime would be A plus
Cx prime.
Okay, you said C. Is that what you said?
Yeah, C e to the 2x
E to the 2x plus
2c.
C what?
2c.
C cubed? Is that what you said?
2c.
Oh, 2E? Is that what you said? No, I can't hear. I'm sorry.
2c.
2C. Oh, yeah. Okay, I got you. X to the
E to the 2x.
E to the 2x. Got it? Plus.
Is it E?
Yeah, it is an E.
Why do we do E and not D?
Okay. I just sort of said that. They don't like to use the D because D is that differential operator.
That's fine.
Okay.
This is confusing. 2 giant E, little e, 2x.
2x. You got it. Okay. What's that?
Never mind. What? We're going to do Y double prime?
Yeah, we got to do a Y double, Y sub P double prime. What would that equal?
2c e 2x.
Got it?
4c x e 2x plus 2c e 2x plus 4 e 2x.
Are you stuck? Okay. All right, good deal. Now, what?
Do we plug in that y double prime
Into your original equation. You're absolutely right. So this will be
2c e to the 2x plus 4c x e to
okay.
the 2x.
Let's do a little bit of a timeout right now. Let's combine like terms, okay?
Yes, sir.
Okay. So that'll just keep it a little
Yeah, I see what you're talking about.
neater and maybe easier,
So we could have 4c
simpler.
e2x.
Okay, wait. Okay, let's look at those terms with only e to the 2x's in them. Oh, we got three of them, don't we?
That's what I'm saying. Like we could do 4c
Okay.
e to
Okay. Okay, I see. Plus 4e, e to the 2x. So let's just do a 4c plus 4e, e to the 2x. Agreed?
Yeah, we could just pull out a 4e to the 2x.
Okay, you want to put the 4 here? Okay.
Can we
You
not,
have c plus e.
can we not do that?
We can. I'm just trying to see if there's an advantage to doing that. I kind of think not, but so let's go back and leave them in there. You may be right. Maybe it'll be a better deal, but
So leave the 4 in there?
I would say leave the 4's in there.
Okay, 4c.
4c plus 4e, e to the 2x, plus 4cx, e to the 2x, right? Yay or nay?
Yeah.
Okay. Minus 2, and now let's do the y prime. Now let's also combine like terms there. Well, the a is just the a. That's the only one there. But now you've got a plus c plus 2e, e to the 2x, right? Plus 2c x, e to the 2x. All right? Minus 3 times, and we just write down that one, ax plus b plus c x to the e to the 2x plus e to the 2x. Believe we got it. All right. And that's supposed to equal 4. Yuck. My thing went out again.
Battery?
No, the plug. Out the.
Is the battery on red again?
Oh, it's been on red ever since, even when I plugged it in. Okay. This is supposed to be 4x minus 5 plus 6x e to the 2x. Okay. All right. At least it's quit beeping, though, so I think that is an improvement over this course.
There's a way you can go in the computer, though, to remove that notification.
What's this
There's
again?
a way to go into the computer and remove that notification.
I don't think so. I mean, that's a warning that your battery's getting low.
You can
They want to
remove
warn.
it, trust me.
Huh?
You can remove it, trust me.
Okay. I bet so, but then I'd probably run the battery completely down. Okay, so I think there's a reason to have it there. All right, so now we need to combine all the things together, and let's see what we've got. Okay? So from the first term, we got a 4c plus 4e. That's times e to the 2x. But let's combine the other. Here's a minus 2 times that, so that would be a minus 2c minus 4e, and that's times e to the 2x. But let's go to the next one, and you get a minus 3e times e to the 2x. So this is all your e to the 2x's, right?
Yep.
Okay. Now let's do those that are x e to the 2x's. So that would be our plus 4c. Okay, there's the first one. And then you got a minus 4c. And then you have a minus 3c. And these are all your x e to the 2x's. Okay? Now let's get the constants. Okay? I'm going to continue underneath. Minus 2a and frankly, that's the only one I see. nope, minus 3b. Okay, those are your constants. And I think we've covered everything now. No, we haven't covered the x's. Okay. Aren't any x's there. There's one here. So I'm going to do a plus. These are maybe do a minus times those. Well, I'll leave that alone. Okay. So here we have a minus 3ax, and that's the only x term that I see. Okay. Now, this is then supposed to equal that. All those combine to be that. Okay, the only term that we have with x's only is a minus 3a here equal to a 4 there, right? So that would produce an a equal minus 4/3. Yes. Okay. Now, with that in place, let's go back and combine a few things together. This coefficient here, well, let's do the other easy one. We got a minus 5 over here, and we've got this. So if a is minus 4/3, minus 2 times minus 4/3 would be positive 8/3. So we have 8/3 minus 3b is equal to, that's all you have over here, is equal to a minus 5. Okay? So let's subtract, well, let's do this. I'm going to rewrite this as 3b is equal to 8/3 minus plus 5. Okay, which would be 15/3 plus 8/3 would be 23/3. Equal 23/3. And then divide by 3, and you got 23/9. So b is equal to 23/9. Let's see if that, yes, look at that. Okay. Now, I need more room. Okay. So what I think I'm going to do is come up here, and we've already dealt with this. And that. I don't think we need this one anymore. And we may not need the one above it either. Oh, we do. I think we do. So let's just get rid of this one. Okay. And we don't need this one anymore. But we do need our complementary solution, although let's not mess with that. We don't need that anymore, or those anymore. We've already dealt with those. And we don't need this one anymore, so we've already dealt with that one. Okay. We basically have just about run out of time, haven't we?
Yes, sir.
Okay. I think we're at the point you could probably finish the problem by yourself, can't you?
Yes, sir.
Okay. So let's do that, and we will begin next time with example 4. Okay? Okay, we'll begin next time with example 4. And I think so far, woo, this is a long section. You can do any of the odds 1 through 25 that are in the back of the book. And we'll stop there. Okay? All right. Now, before you go, I've got a gift for you because y'all were so nice today, okay? I'm going to give you your final exams. Actually, they're just test 3. I know you don't want the key, so
Oh, I love the key.
oh, you would.
Oh, it's
Really
just 5
ugly
questions. It's just 5 questions?
writing. Again?
It's just 5 questions?
Yeah, but in multiple parts.
Yeah.
I know you can do number 1 right now because we've already covered that. You may not be able to do all of 2. You may be able to do the first part of 2 on the undetermined coefficients or not. So don't sweat it. We'll finish this hopefully next time. And then you can do number 3. I know you can. And I know you can do number 4. Okay? Number 5 you might be able to start doing now, but we haven't done all of those, so you might want to wait on those, but you can start. Okay. All right. Now, all of you have your second test already, right?
Yes, sir.
You got it? Okay. So this is test 3.
Okay, so you're saying we possibly can't do question 1, but we can do 3?
No, number 1, you can do those.
No, I said 2. I meant 2.
Okay, 2, you might be able to do the first part on undetermined coefficients, yes or no, I don't know. Or you could wait till we finish doing this next time. Variations of parameters, you can't do those because we haven't even started those. So, okay. But then number 3, 4, I know you can do, and number 5, you might be able to start doing that.
Okay.
Good deal.
Okay, I just find it odd that you can do 3 and 4, but we can't do 2. I thought this would be more.
What's that?
Oh, no, never mind.
Yeah, okay. All right, but I need your others too.
Yeah.
Right. So you don't have to worry about this one until you get the others done. But once you get the others done, you can start working on the ones I said. Okay.